Okay, guys, we're going to talk about environmental chemistry this morning, and we're going to take a look at what goes on in our environment. Now, we have what we call our atmosphere. So, our atmosphere is made up of different parts. You got your troposphere, your stratosphere, your mesosphere, and your thermosphere. Now, the temperature does vary greatly with altitude within the troposphere, and that's where we live. And as altitude increases, pressure decreases. Pressure decreases with altitude in the atmosphere. Now, the composition of the atmosphere, uh, all of the gases, they are not uniform. Heavier gases tend to sink in the atmosphere, leaving lighter ones to come to the top. Near sea level, the majority of the atmosphere is nitrogen and oxygen. Now, when it comes to nitrogen, it's usually unreactive due to the bond energy with breaking the bonds between N2. Now, oxygen has a lower bond enthalpy and therefore is more reactive. Oxides of nonmetals are acidic. Oxides of active metals are basic. Now, there are certain type of photochemical reactions in the atmosphere. Um, so we have our outer defense, and we talk about it, our ozone, save our ozone and everything. Our outer defense of the earth technically protects against radiation and high energy particles occurs. Now, chemical changes occurs with that is called photodissociation or photoionization. Now, photodissociation is a rupture of the bonds due to absorption of a photon. Ions are not formed. Radicals having unpaired electrons are often formed. One of the most important reactions in the upper atmosphere is the photodissociation of oxygen molecules. And you see the reaction down here. Um, Now, photoionization um, happens when you have molecules in the upper atmosphere. They absorb solar radiation. They emit those electrons. This is photoionization. Now, when this happens, you form a cation. Now, our ozone absorbs much of the radiation, anywhere between 240 and 310 nanometers, and that protects us from UV radiation. Now, it forms the reaction of molecular oxygen with oxygen atoms produced in the upper atmosphere by photodissociation. So it's O plus O2 give us O3. The ozone layer occurs in the stratosphere at an altitude of about 25 kilometers. Now, the Earth's atmosphere can be changed by natural events, volcano eruptions, releasing of CO2 from ocean, and lightning. There are other things that can happen too. You can have ozone destruction by CFCs. You got combustion leading to CO2, SO2, and other nitric oxide that can increase. So, volcanoes, CO2 from ocean, lightning, all these different things that can really destroy the Earth atmosphere. And while we've been going through this pandemic, what we have noticed is since everybody been staying at home, the air has been a lot cleaner because we have reduced CO2 emissions. Now, in 1974, Rowland and Molina discovered that chlorine from chlorofluorocarbons, or CFC, may be depleting the ozone in the upper atmosphere by chemical means. Now, despite a ban, the CFCs have already made their damage done. It's going to keep doing it because of the chemical nature of the CFCs. So it's going to keep doing it for a while. It already has hurt the ozone. And so a lot of countries have banned this, but the ozone damage has already been done. But Like I said, right now, Mother Nature is taking the time to replenish itself. Now, CFC was used for years as aerosol propellants and refrigerants. They are not water soluble. They don't degrade naturally. The carbon chlorine bond is easily broken by light, and the wavelength don't have to be big, 190 and 225 nanometers in the atmosphere. And that's where the ozone layer exists, in the stratosphere. The chlorine atoms are formed, react with ozone, and it's chlorine plus O3 would give you chlorine oxide plus O2. So that's how it breaks down. Now here, the rate of conversion of ozone to oxygen gas is dependent upon ozone concentration and chlorine atom content. So the more chlorine atoms you create, the more ozone you destroy. Now, there are different pollutants in the average city, and this is just a table here. This is typical urban environment. It assumes no major smog problems in the city. Now, normally with sulfur dioxide, the values is low. That can be a really big hazard. Now, SO2 is a byproduct of burning coal or oil. It reacts with moisture in the air to form sulfuric acid. This is primarily responsible for acid rain, and nitrogen also contributes to acid rain. High humidity and rainfall causes corrosion to building materials, so that's what happens. Now, there are other means to prevent emissions from different types of chemical plants. They like to use what we call scrubbers. Um, their powder limestone can be added to the furnace of a power plant, is converted to calcium oxide, which reacts with sodium dioxide to make, um, and I think it's CaSO3. The gases can pass through the suspension of calcium oxide with the same result. So basically, what they're doing is they put it in there, and it makes this. They basically just scrubbing and trying to capture the sulfur. The sulfur dioxide in the air is really bad for us, and so that's what they're doing, is trying to capture it. So it's called a scrubber. If you've been down there on Highway 43 near some of the chemical plants, a lot of them have scrubbers in which you will see the limestone and everything in there. Now you have photochemical smog. That brownish gas that hangs over large city is mainly nitrogen dioxide, NO2. It's from the oxidation of nitric oxide, a component of car exhaustion. On the news yesterday, they were just talking about how some areas, especially in China, um, and in some areas, that the smog has actually cleared, and that's what it looks like. The nitrogen oxides are just some components of photochemical smog. Ozone, carbon monoxide, and hydrocarbons also contribute to air pollution that cause severe respiratory problems in many people. There, what you call a thermal balance. The Earth has to keep a balance with its surroundings. The planet radiates heat to space and gains heat from the sun. You can also have the greenhouse effect. Carbon dioxide and water vapors absorb some of the radiation from the surfaces. These gases are known as the greenhouse gases because they will cause the retention of heat inside the atmosphere, much like a greenhouse gas keeps in heat. Now, there's effects of increasing amount of carbon dioxide. Water is the major absorber of radiation. Its levels vary by location and time of year. The CO2 levels from human use of fossil fuels, primarily coal and oil, have increased drastically over the last century. This has caused an unnatural increase in atmospheric temperatures. Most of the processes depicted depend on the phase changes of water. And this is basically the global water cycle. You guys hear about this a lot in biology. So what happens is you have water stored in the oceans. It gets evaporated. It goes up into the atmosphere. Is condens- uh, condensation happen, and then when condensation happen, it comes in as rain, or either it goes into ice and snow, and then what happens is you can get snow melt, leaves run off in streams. You can have evaporation of fresh water. It can go into groundwater and discharge, and then what happens is you got groundwater storage, and then it flows back up the out to water into the oceans. 97.2% of all the water on the earth is in the ocean. The vast ocean contains many important compounds and minerals. The ocean is a source of sodium chloride, bromide, and magnesium. Now, absorption of carbon dioxide in the ocean plays a major role in our global climate. Now, fresh water is about 6% of the water on the planet. The United States uses fresh water for agriculture, hydroelectric power, industry, household needs, and drinking water. The use of water as dissolved materials, including human waste, it becomes increasingly expensive to guarantee our water supply. Groundwater is fresh water under the soil in aquifers. Approximately 20% of the world's fresh water is groundwater. When used, these sources are not readily generated. It takes a long time for water to penetrate the rock layers that create an aquifer, and not all groundwater is potable due to the ions in rock formation. Some will contain poisons like arsenic in high levels. So some of it is not drinkable. Now, you can have dissolved oxygen and water quality. Now, the amount of O2 in water is an indicator of the water quality. When you have bacteria act on biodegradable material, they use oxygen. Excessive amount of biodegradable matter can result in the inability of normal animal life to exist. This also lead to anaerobic oxidation conditions, which give off really bad odors. And that's what you see right there is sulfur on the top of the water. Excessive plant nutrients can use to eutrophication or excessive dead plant matter in water, and that's what you see there. Now, there are different water purification techniques. Now, seawater has too high of a concentration of NaCl for human consumption. It can be desalinated through reverse osmosis. And what happens is water flows through a semi-permeable membrane from regions of low salt content to regions of high salt content. If pressure is applied, the water can be forced through a membrane in the opposite direction, purifying the water. Water purification, municipal water treatment, steps to purify the water for a municipal supply, filter large particles using a screen. Um, Calcium oxide and aluminum sulfate is added to remove those small particles, again scrubbing it out. Water is aerated to increase the amount of dissolved oxygen and for oxidation of organic impurities. Ozone or chlorine is then used to disinfect the water. Yes, we even disinfect our water. As one such solid filters remove sediment and bacteria, and that's what the life straw is called. Iodine impregnated bees kill viruses and bacteria. Charcoal removes iodine smell and most remaining parasites. So they got straws that purify water, and that's what they do in parts of Africa. Now, Another part is looking at green chemistry. The Earth can largely be considered a closed system which exchange energy with the rest of the universe. For humanity to thrive, however, we need to keep our natural processes in balance with the Earth's natural processes. This is the basis for green chemistry. It is an initiative that promotes design and application of the chemical products and processes that are compatible with human health and preserves the environment. Prevention is better prevent waste to clean up after it has been created. We have atom economy. Methods to make chemical compounds should be designated to maximize the incorporation of all starting atoms into the final product, and then less hazardous chemical synthesis. Wherever practical, synthetic methods should be designed to use and generate substance that provides little to no toxicity to the human health and the environment. That's what they do in green chemistry. A lot of people, like, I know y'all probably hear me talk a lot about going tiny, and going tiny in some cases is living green. Now, what you do is you can also design safer chemicals, um, and, and this is the same thing, living toxic free, safer solvents and auxiliaries, and then the design for energy efficiency. So energy requirements should be recognized for their environmental and economic impacts, and you have to minimize that. And so what they're saying is carry out things at room temperature and standard pressure. Uh, Safer solvents, uh, use non-toxic. A lot of people don't like to use paints that smell in their house. Um, Other things that might have other chemicals that can be released into the air. Now, you could also use different type of renewable feedstocks. Raw materials should be renewable whenever technical and economically practical. Reduction of derivatives, and then catalysis. Um, if you have catalytic reagents, they improve yields within a given time with less energy and are therefore preferred. Um, Other principles design for degradation. Chemical products should be designed so at the end of their function they break down to innocuous products that do not present in the environment. You have real-time analysis for pollution prevention and inherently safer chemical for accident prevention. Reagents and solvents used in the chemical process should be chosen to minimize the potential for chemical accidents. And what is examples of green chemistry? Preparation of styrene using toluene and methanol. It's a one-step process. So you replace the chlorofluorocarbon solvents or CFCs with liquid or supercritical CO2. Those are safer solvents. Hydroquinone production by a new method that recycles byproducts, and we heard a lot about hydroquinone in the news as of lately for medicine. So that's what they're doing there.